Next, we're going to talk about joint probability distributions. These are used when we have more than one random variable of interest, and we are interested in how a probability distribution can characterize a particular population that involves more than one variable of interest. So to give you some brief examples of where this kind of a case occurs is that, let's say you're interested in the white blood cell count for patients at times 0, 1, 2, 3, 4 hours. And in that particular case, for each time point, we have a particular random variable. And we might want to understand probabilities associated with these white blood counts. Maybe let's say after a particular medication has been administered, we might be interested in understanding probabilities associated with those white blood cell counts. Another case is, let's say we're interested in the tire wear for all 4 tires on an automobile. In that case, we have 4 different random variables. The scores for each part of a nationalized standardized test, and the amount of pressure put on both ends of a piece of lumber until it breaks. So in that case, we would have 2 random variables. And I give you these examples because these examples do actually occur. So just recently, for example, I came across a paper that looked at how one could, with a probability distribution, quantify probabilities associated with breaking lumber in this way. So the word joint with probability distribution then means I have a set of random variables. I'm interested to jointly look at probabilities associated with them. So for most of this section, we're going to consider the case where we have just 2 random variables, because once we understand how to work with 2, we can go to 3, we can go to 4, and so on. So a joint probability distribution for 2 discrete random variables, x and y, is denoted as f of xy. So notice this is a function of 2 variables. And what f of xy denotes simply is the probability that our random variable x is equal to a particular quantity intersect our random variable y is equal to a particular quantity. So this relates back to what we saw at the very beginning when we were talking about probabilities, when we had probability of A intersect B. So that probability is what this f of xy is actually denoting with respect to discrete random variables. Note that we can more simply, or what you often see more simply done is, instead of putting that intersect symbol in there, people just simply put a comma, and they'll just say it as the word and. So the probability of x and y, for example. F of xy is always going to be greater than or equal to 0 for all possible values of x, all possible values of y. And if I were to take the sum of over all the possible values of x, sum over all the possible values of y, f of xy, I get 1. This just corresponds to how the sum of all possible things that can happen in terms of the corresponding probabilities, that sums up to 1. Now, with respect to a continuous random variable, we can have a joint PDF as well. F of xy is always going to be greater than or equal to 0 for all x and y. To find probabilities, now we replace summation with integration. So if I sum over all, if I were to integrate from negative infinity to infinity for x, integrate from negative infinity to positive infinity for y, f of xy dx dy, I will get equal to 1. Now, since we have 2 random variables here, rather than looking at the area underneath the curve, we're going to be looking at the volume underneath a surface. And if I'm interested in a particular probability that involves x and y, and I'm wanting to know, are they within a particular, let's say, area or some region, let's say maybe between, we'll see an example coming up shortly where maybe x is between 0.8 and 1, y is between 0.8 and 1. How do I find that probability? Well, I integrate with respect to that region, f of xy dx dy. So let's take a look at an example. This is very simple. Let's say I roll a pair of dice. X is going to be a random variable denoting the result from the first die. Y is for the second die. They are discrete random variables because with a die, typically there's only 6 sides. In that particular case, we know that all possible outcomes of the first die and second die are equally likely. So I get a 1 and a 1, I get a 3 and a 4, I get a 6 and a 6. All possibilities are equally weighted. Have an equal probability as long as the dies are not weighted in some way. And so f of x, y is equal to 1 over 36 for each possible value of x and y. 0 for any other case, because you can't like roll a 7 on one die. Can't roll a -1. Note that if I were to sum up all those corresponding f of x, y values, then I would get equal to 1. Okay, that's a simple example. Let's take a look at an example now dealing with continuous random variables. Let's say that I have grades for 2 courses. So let's let x be a random variable denoting the grade in a math course, y be the grade in a stat course. And when I mean grade, x could be anywhere between 0 and 1, same as y, where like a value of 0.9 means you get a 90% grade for a particular course. Now, where would this be of interest? Let's say we look at the prerequisite for our course that we're taking. It's the grade that you got and the grade that eventually that you'll get in our course. And so we might be interested in probabilities associated with these 2 different grades. And where could that be of interest? Well, we'll look at a case a little bit later on where, since this particular course is a prerequisite for the course that we're interested in, or our course, I should say, one can maybe use the grade in our course to have some idea of what will happen. The grade in the prerequisite course, use that as a way to understand what will happen in our course. More on that later. Okay, so let's say that this is what the joint PDF is. F of x, y is equal to x squared plus 2 times y squared. This is for 0 less than x less than 1, and 0 is less than y less than 1. Let's look at a plot. Whenever I have a PDF, whether it's just for 1 random variable or 2 random variables, I always like to look at some kind of picture so I have a better idea of what's going on with it. And so, unfortunately, in R, there is not like a nice curve function that one could use to draw the PDFs like we were before. But there is, through doing some web searches, I did find a function that somebody wrote that's not in R itself, where this function is basically equivalent to the curve function, but now it graphs a surface in 3 dimensions. And to use this particular function, we need to use a package called RGL. This is a package that you'll need to install yourself so you can actually use it. And in our introduction to R set of videos, we talked about how to do that. Now, the actual function that I want to plot my PDF, I'm going to create a function in R to represent it. So it's going to be fxy, for the lack of a better name. The function is xy, or I'm sorry, the function has 2 arguments to it, x and y. And then inside the squiggly brackets there, I put what f of xy actually represents. And we can actually test it out. So if a grade was 0.9 for x, grade was 0.95 for y, If I pass that information into this particular function, then I get 2.615. And what this is going to represent then is the height of this surface that we're going to be plotting. Now, to do the plot, again, I found this particular function called curve3d, which is kind of the equivalent of curve for just 2 dimensions. You're not responsible to understand the contents of this function. Rather, what you're responsible for is how to actually use it. So I'm going to go ahead and highlight that and run it so I can get the function inside of R. To do the 3D plot, I need to first open up a 3D graphics window. So let me go ahead and do that. Open up in a different screen. Okay. And then to do the plot, I say curve 3D. F2 is the actual function I want plotted, fxy. And then to say, well, where do I want to plot with respect to the x range or the x-axis of a 3-dimensional plot? I say x range, I want to plot between 0 and 1. For the y-axis range, between 0 and 1. and then I'm going to make the color of the surface red. So let me go ahead and do that. And here's the plot that we get. The red part there, that represents this f of x, y. And inside this plot, I can actually spin it, I can rotate it, I can zoom in, zoom out, and so on. So if I just take my, if I click on my left mouse and hold down on it, and then move my mouse, you can see how the plot is rotating. And so you get a better idea of what the surface looks like. So here, if you see where my mouse is, we have the y-axis. Here's where the x-axis is, and then the z-axis goes up. This is what f of x, y is being plotted on. And so I can spin this totally around. Now, if I look at, let me come up here. Now, as we talked before, when we only had one random variable, the area underneath the curve, we would say, and above, let's say f of y is equal to 0, represents probability. Now, in our particular case here, the area underneath the surface and above f of x, y equal to 0, if you imagine a plane at f of x, y is equal to 0, that equals probability, the volume underneath there. And so if I spin this around, see where my mouse is here, all this right here, this area, I'm sorry, the volume underneath this surface, but above f of x, y is equal to 0, represents probability. That whole volume is equal to 1. Now to zoom in, zoom out, I can use my right mouse. And if I just click on my right mouse and then move my mouse up, we can see that I'm zooming out. If I move my mouse towards me, I'm zooming in. Perhaps a little bit too much right there. Okay. So that's what the surface looks like. And again, we're going to use this now to find probabilities shortly. Sage can do this kind of a plot as well. So let me come on over here to Sage. Restart my project here. Okay. So now since I have two variables of interest, I need to use, I need to say var, just like what we did before, but now within the quotes, I can put x and y. I can put a space between the two. I'm going to make assumptions about what x and y can be, 0 to 1. And then simply, I type in f of x, y, as you might expect. You know, Sage recognizes that x and y are elements or variables inside this function itself by using this kind of a syntax there. And if I remove that comment right there and run the whole thing, Plot3D does the three-dimensional plot. And notice what I'm doing a plot of f of x, y. And to specify, well, what are the x possible values, I put parentheses, x, comma, 0, comma, 1. Go back up. For the y values, I put them together again in a parentheses here, y, comma, 0, comma, 1. And then to have some grid lines on the plot, I simply put mesh equal true. And it's hard to see necessarily for us here because I've really zoomed in on my browser here, but you can see I can spin this plot, zoom in, zoom out, just like how I would with R before. Okay. Now, how would you actually show then the volume underneath that surface is indeed equal to 1? And that's where, again, we use integration. So if I integrate over all possible values of x, 0 to 1. Integrate over all possible values of y, 0 to 1. X squared plus 2y squared, my f of x, y. Do that integral, do it on your own, you do get 1. If I were to do this integral in R, this would be a lot more difficult. Unfortunately, two-dimensional and higher integration in R, I don't think the facilities are there to make that easy. But in Sage, it is fairly easy. And you can do what you might maybe expect. Suppose we look at this first part of this integral here with respect to x. That right there. That's going to be equal to, in Sage, that middle integral there, integral of f of xy with respect to x, 0 to 1. And then to do the outer integral, I just embed that all into another integral called the integral function, with integrating with respect to y, 0 to 1. And if you do that, you do get 1. So that's good. Okay. So let's say that I wanted to find the probability a randomly selected student receives an 80% or higher in both courses. How would I represent this in a plot? So let's go back to my plot that I did in R. So what I'm looking for is the probability of being greater than 0.8 for both x and y. And how is that represented in our plot? Well, right here, if you see where my mouse is, I have the x-axis. Over here, I have my y-axis. And basically what I'm doing is I'm looking for the volume that's underneath this curve from x equal 0.8 to 1 and also y equal to 0.8 to 1. And I have a screen capture of that particular plot now, so I can draw on it nicely. And so if you can imagine me doing this in 3 dimensions here, which can be difficult. So on the f of x, y is equal to 0 plane in 3 dimensions, what I've done here is I've actually kind of drawn out where I would have an x and y within this region. And if I project this up in my plot, fortunately, I can't draw straight lines very well. But basically, if you could imagine that whole region that I just drew as colored in, that will be the corresponding probability that I'm interested in. I'm interested in the area underneath that surface. So let's get back to the notes here. And we'll look at how to do that shortly. Now, just like what we had for one random variable when we had CDFs, cumulative distribution functions, you could also have a CDF when you have more than one random variable, so a joint CDF. And the definition is hopefully what you wouldn't necessarily expect. So my CDF is denoted by capital F now, capital F of x, y, and this is with respect to a discrete, this is respect to continuous random variables here, x and y. What I'm looking for is the probability that my random variable x is less than x, and probability of my random variable y is less than or equal to little y. How do I find that? Again, I use integration. Integrate from negative infinity to x, and also integrate from negative infinity to y. And I'm going to integrate f of ts dt ds, where I've simply replaced x and y by t and s to avoid confusion between the limits of integration and what we're integrating over. With respect to a joint, with respect to a discrete random variable, now all you would do is simply do sums. Here's a question. So how can we find the joint PDF then from a joint CDF? Well, before, when we had just one random variable, let's say it was y, I would take the derivative with respect to y, f of, capital F of y, and that gave me little f of y, my PDF. Now here, since we have we have 2 random variables, now what we need to do is take the partial derivative with respect to x, take the partial derivative with respect to y for this capital F of x, y, and then you get the joint PDF. Okay. Now, how do we get, or let's say that we're interested in maybe just one of the variables rather than both. Could we just look at one of the variables, look at probabilities associated with that? And the answer is yes. And the way that you do that is you just look at what's called the marginal PDF. So let's say that I'm only interested in x for some particular reason. And so if I want to get the PDF, marginal PDF for just x, let's call it g of x. Then all I would need to do for a discrete random variable y is to what's called sum it out, meaning you sum over all possible values of y, f of x, y, and then you're going to get the PDF for just x itself. For a continuous random variable, you now do what's called integrate it out. So g of x then is the integral from over all possible values of y, f of x, y, dy, and there's your marginal PDF. If you want, let's say now the marginal PDF for y, well, what you do is do the same thing as what you were doing before. Now I'm going to sum out all possible values of x, or I'm going to integrate out all possible values of x. Okay, let's take a look at an example. We're going to go back to that rolling a pair of dice example. Here's our joint PDF. Now, if I want to find just the marginal PDF itself, meaning what I roll on that first die, the corresponding probabilities, what I need to do is sum out all possible values of y. In other words, sum over y equal 1 to 6 f of x, y. And because this is such a simple joint PDF to work with, what this ends up happening is that when y is equal to 1, I have a 1 over 36. When y is equal to 2, I have a 1 over 36, and so on. And I do that 6 times because y is equal to 1 to 6. And what do I get? Well, you sum those up and you get 1/6. And hopefully that makes some sense to you that the marginal PDF for one die is 1/6. So what that means is the probability of getting a 1 for the first die is 1/6. The probability of getting a 2 for the first die is 1/6, and so on. This is obviously a very simple example. We'll have more complicated examples later on, whereas your intuition will not necessarily tell you what maybe the answer is beforehand. And of course, we could do a similar thing for y as well. Okay, so let's talk about the grades for 2 courses example, though. X is a grade for the math course. Y is a grade for the stat course. Here's my joint PDF. Let's say I just want the PDF for the math course. In other words, I want the marginal probability distribution function for x. How do I do that? Well, here's my g of x. I'm going to integrate out y. Y ranges from 0 to 1, so I integrate from 0 to 1. X squared plus 2y squared. Go through the math. You get x squared plus 2/3. That expression there now gives me probabilities just for the math course itself. We don't care about the stat course. We don't care about y, just for the math course. Now, with respect to the marginal PDF for the stat course, now I integrate out x. So I take the integral from 0 to y of x squared plus 2y squared dy. I'm sorry, that should be dx. And I go through the integration there, and I get 1/3 plus 2y squared. Let me just make a note to myself to correct this in the notes. Okay. Let's look at some plots. So similar to what we've done before, I'm going to use the curve function now to plot in 2 dimensions. First, I'm going to plot g of x. So for my EXPR argument, I put in what g of x actually represents. X ranges from 0 to 1. And I'm going to include some other arguments as well to make the plot look nicer. Then I'm also going to plot h of y. So for my EXPR function, I put what this h of y is. But remember, in terms of our syntax, whatever I put in the EXPR argument, it has to be as a function of x. So where I had a y before, I put in an x. Then I add a horizontal line at 0, and also I put a legend in there so that we can make sense of what's being plotted. So here's my plot. Red represents g of x, so the math score. blue represents the stat score, h of y. And so we can see here, and first of all, I should mention, the reason why we can plot both of the PDFs on the exact same plot is because it just so happens that x and y range have the same numerical range, 0 to 1. There might be other examples out there, or I'm sorry, there will be other cases out there where you have a random variable that maybe is measured from 0 to 100, another random variable that's measured from, let's say, 2 to 3. And you wouldn't be able to do a plot very well like that. But since they are measured on the same numerical scale, we can now do some comparisons. So if I'm interested in, well, what's the probability of receiving an 80% or greater in these courses? Again, I can look at area underneath the curves. So for the math course, here's the corresponding probability of getting a score of 80% or above. Now the stat score, we can see we can go up a little bit higher and also get the corresponding area. And so again, we're looking at the area underneath the blue curve all the way down to that horizontal line at 0. And so we can see that there is more area from the blue line down to the y-axis value of 0 than there is from the red line down to the y-axis of 0. So therefore, the probability of getting an 80% or above in a stat course, that probability is higher than it is for the math course. Now, how would I do these integrals in Sage? Well, obviously these integrals are not too difficult. You might not need to, but if you were to do that, simply you take where you had your f of xy before. I'm going to integrate out y. Y ranges from 0 to 1. I'm going to put that into an element or a function called g of x. Type out g of x, and there is exactly what we had before. You can do the same thing for h of y as well. Note that you will not be able to do this very well in R, so that's why we're not talking about it there. Well, let's say that I want to actually use now integration to find that probability that was represented in that previous plot. Suppose I want to find the probability x is actually greater than 80% or 0.8. How would I do that? One way is just simply take your marginal PDF for x, g of x, and integrate from 0.8 to 1. If you do that, you get 0.296. Another way that you could do that is instead start with the joint PDF, integrate from 0 to 1 for y, because notice we're not saying anything about what this particular score is for y. So we integrate it out, and then we do that integral of 0.8 to 1 dx. So in other words, this part right here is our g of x. And I can do this in Sage. You can take a look at my corresponding code there. To get the probability then associated with the stat course or y, I want to find the probability y is greater than 0.8. So I take the integral from 0.8 to 1 of h of y dy. Do the math, you get 0.392. So if we go back to our previous plot, let me do some erasing here. Okay, so the area underneath the curve, the blue curve, that area is 0.392. Let me get a new pen out here. And the area underneath the red curve, fortunately it's not showing up now. Well, the area underneath the red curve down to the y-axis value of 0 is actually then 0.29. I believe that's what we had. Let me just go back. What do we have? Yeah, 0.296. So maybe I'll denote it like this, and I'll denote that by that. Sorry, it's kind of messy. Sometimes, fortunately, my tablet PC doesn't work as well as I would like when I'm also recording at the same time, because it takes up a lot of CPU power. So that's why I was having problems writing on the screen, why sometimes I have problems erasing the screen too. Okay. So the main thing is we saw that what we saw in terms of the plot, in terms of the areas, why we saw one area larger than the other, that's confirmed by actually doing the integration. Now let's take a look at this particular case. This is what we actually looked at earlier. What's the probability that x is greater than 0.8 and y is greater than 0.8? So essentially you get b's in both courses. If you remember, this corresponded to this volume underneath the surface that we were talking about before. So how would I find that probability? Well, now we have to work with f of x, y directly. And we want to find the integral from 0.8 to 1 for x, integral from 0.8 to 1 for y, excuse me. If we go through all the calculus there, we get 0.0976. And so let's go back to our plot here. And so that what that means is that that volume is 0.0976. If we look at that corresponding to the rest of the plot, we can see that, yeah, there's a lot of other volume available outside of this small region itself. So it makes sense to have only about a 10% probability of getting B's or higher in both these courses. To do the integration SAGE, very similar to what we saw when we looked at the area underneath the whole surface was equal to 1. We have two uses of the integral function there. Here's my f of x, y. I chose to integrate over y first. You don't have to do that. You could integrate over x first instead. And I'm integrating from 0.8 to 1. And then after that integration is done, then we integrate the result once again, which will be a function of x. We're going to integrate from 0.8 to 1 over x. Okay, here's another question. What's the probability of getting a B or better in at least one of the courses? In other words, I can get a B or better in math, where maybe in stats I get something lower. I get a B or better in stats, where maybe in math I get something lower. Or I can get a B or better in both courses. This then corresponds to something that we talked about earlier in our course, working with unions of events. So the probability of A union B, if you remember that, is the probability of A plus the probability of B minus the probability of A intersect B. Now, with respect to this joint PDF, we need to do the same thing. So the probability of x being greater than 0.8 union y greater than 0.8 is equal to the probability x is greater than 0.8, which we already found to be 0.296 before, plus the probability y is greater than 0.8. We found that to be 0.392. And then we just found the probability of this intersection as well to be 0.0976. And so the probability of getting a B in at least one of the courses then is 0.59. Okay. Now, also in the past in our course, we talked about conditional probabilities such as this, the probability of A given B. And we said that's the probability of A intersect B divided by the probability of B. We can also talk about that same kind of concept now with respect to PDFs. So I might be interested in the conditional PDF of Y given X is something. For example, let's relate this back to, let's say, the math and stat course. Suppose you get a score of 80% in your math course. Given that, that says something about perhaps how you would do in the stat course, since math and stats is somewhat related. And if you do good in your math course, then what's your probability distribution with respect to your stat course? That's where that could be of interest. A very similar case is, let's say you got a 95% in the prerequisite for our course. Given that 95%, now you would want to find what's the probability distribution associated with our course. What's the probability, for example, you might get a B or better in that. And that's what that's what a conditional PDF can help you find. So the way that we denote a conditional PDF is like this. f for function, f of y given x. So that line that we saw before in our class is pronounced as given. So given a particular value of x. And this is what this conditional PDF is. You take the joint PDF, divide by then the marginal PDF for what you're conditioning on, that particular random variable, x. Notice how this is so similar to what we had before when we were talking about in our section just regular old probabilities. Probability of A intersect B was our joint probability. Probability of B was our marginal probability. Also, one could look at the conditional PDF of x itself given a particular value of y. And so you could have f of x given y. That's equal to the joint PDF divided by the marginal PDF for y. And let me just emphasize something here. So you see this little x, you see this little y. That means you're conditioning on a particular value of x or y. Relating to our grade examples, little y could be, let's say, 0.85 for a stat course. Given you got an 85% in stats, let's find the probability distribution for the math course. Okay, so let's go back to this grades for 2 courses example. Now, if I want to find the conditional PDF of y given a particular value of x, then in that case, again, I take the joint PDF, x squared plus 2y squared, divide by that marginal PDF, g of x, which we found before to be x squared plus 2/3. Sometimes you'll be able to simplify this a little bit further in terms of making it a nice mathematical expression. Here, it's not necessarily, you're not going to be able to really simplify it much. Notice then this is defined over all the possible values of y that y can take on. Again, you're conditioning on a particular value of x. This could be, let's say, 0.75. And in fact, that's what I have next in the notes. So let's say you did get a math course grade of 75%. So we would put that 0.75 in wherever you see x. And now here is our conditional PDF. This is what it looks like graphically. So again, if I want to find the probability of getting a B or better than in my stat course, I just simply find the area underneath the curve there. But also what we can see with this conditional PDF, it's a function of whatever that x value is. So this plot is going to change depending upon what that x value is. And that's the purpose of, I'm going to jump ahead here, what's on page 19. So before we had x equal 0.75. But we can see that as x changes, so does the PDF, so does the plot, so do the corresponding probabilities. So we can see in this particular case, and this isn't necessarily a realistic actual PDF that I'm using here, we can see if you want to maximize, let's say, your score in stats, well, do poorly in math, and you're going to have a higher probability of getting a B or better. Okay, so let's go back. So let's say I want to find the probability that you get a B or better, 0.8 or above in stats, given that you did have that 0.75 grade in math. Well, that's what this area, again, represents. I can now integrate from 0.8 to 1 of f of y given x, go through the integration, and you get 0.3562. So in other words, this area here is 0.3562. How can I do this in Sage then? Unfortunately, there isn't a nice way in Sage to say, hey, I have a conditional PDF to work with. Instead, what I did here, for example, I created a function which I called f given x, where it's a function of y. And based upon what I had for f of x, y before, and g of x is what I had before, here is then the corresponding conditional PDF. Using that conditional PDF then, I can do, I can integrate just like I did before. So if I integrate my function for over y from point A to 1, this is what I get. Now notice here though, Sage leaves us in terms of what x is, because we're saying given a particular grade, given a particular value of x, but we haven't specified what that particular grade is. How can you do that? Well, if you want to, you could just simply put in 0.75 in there for x. Or maybe perhaps a little bit more of a slick way to do it is that suppose you save your results from using the integrate into something called RES for results, for the lack of a better name. Then use the function subs, do res dot subs. We saw something similar to that before when we used the dot end function in Sage. Res dot subs x equal 0.75. Subs means substitute. So wherever you see an x, substitute for 0.75, and here is then that corresponding probability. Do note that, and I think I failed to mention this previously when we talked about Sage, whenever you see one of these functions that you can put after a particular value, like .n, .sub, those are often referred to as method functions in Sage. Okay, let's see. I think we've talked about most of this before. Okay, so bottom page 20. Now, in the past, in our course, we talked about independence between two events. So if we had two events A and B, probability of A intersect B is equal to the probability of A times the probability of B if two events were independent. We can have the same thing here now in terms of PDFs. So x and y are independent if f of xy is equal to the product of the two marginal PDFs. Also, what that means for us, though, is something similar to what we also saw before. So before we saw the probability of A given B is equal to the probability of A if A and B were independent, or equivalently, the probability of B given A was equal to the probability of B if they were independent. We can have the same thing here now with conditional PDFs. So f of y given x is equal to h of y. F of x given y is equal to g of x if we have independence. Now, we can extend the idea of having more than two or more random variables, and we can extend it to the idea of independence. And this is very useful for us in what we will do later in our course. And let's say if we have x1, x2 down to xn as potential random variables. Each has a particular marginal PDF. Let's call it f of xi to be general for I equal 1 to n. Then if the x's are independent of one another, then the large joint PDF itself is just simply the product of these marginal PDFs. Again, we will use that result later in this course. So let's go back to the roll pair of dice example. Let's see if we have independence, meaning what happens on that first die is it independent of what happens on the second die and vice versa. And so here's our PDF that we saw before. We can get the two marginal PDFs as well. And if you take these two marginal PDFs, multiply them, guess what? You do get that joint PDF back. This is an extremely simple example. That's why this works in this particular case. So indeed, x and y are independent. But let's also take some time about, why is this useful to know independence? Well, as we saw before, this is just in general, not necessarily with this example. Oops, I got the wrong file up. Okay. What we saw before is that looking at, let's say, probabilities associated with this three-dimensional object, that was a lot more difficult than what it was when we were plotting in 2 dimensions, when we had a marginal PDF, or when we only had one random variable of interest. And so we can see that as we get more random variables to work with, the problem becomes a lot more complicated. And so it would be nice if we could just work with these marginal PDFs that are just dependent upon one random variable at a time. That will simplify our lives. And so that's why often we are interested in independence like that. It's going to be a lot easier to think of probabilities associated with one random variable than maybe with 10 at a time. Okay. So let's go back to the grades for 2 courses example. Here's our joint PDF again. Previously, we found these marginal PDFs. Let's multiply these marginal PDFs together. And if I were to do that, and please work through this on your own, you get this kind of an ugly looking result there. And you're not going to really be able to simplify it any further, that expression. And so you can see that it is not equal to what we had for the joint PDF. So in this particular case, the 2 random variables are dependent of one another. So it depends upon what x is. Y is going to change. And we saw that before. In fact, let me go back. We saw that in that plot. Oops. Having problems erasing again. Hold on a second. We saw that as x changes, my conditional PDF changes as well. Thus, y is dependent upon x, and also vice versa. If x and y were independent, then wherever x is, I would have the same exact curve plotted here for my PDF, my conditional PDF for y. Now you might be wondering though, well, how much of a dependence is there between x and y? You know, if we relate it to that grade example, you might want to know is your stat grade closely related to what your math grade is, or is it only maybe a little bit? And that might affect, you know, your choices of would you actually take the stat course based upon that. If you weren't necessarily taking them at exactly the same time, you took the math course first. Let's also take a look at in 3 dimensions about what this kind of dependence actually means. And so what I have here, and don't worry about having to reproduce this plot on your own. What I have here is a plot of our surface that we had before in red, which was assuming correspond to our f of x, y, where we did have dependence. In blue here, what I decided to do was plot what the surface would look like if g of x times h of y was actually equal to f of x, y. In other words, that we did have independence. So the blue represents g of x times h of y. And we can see as I spin this plot around that the surfaces are definitely different here. That it does matter if you have, it does matter what one of the grades are for what the other grade will be. And in fact, we can see that if we did have independence here, again, that's represented by the blue curve. Let me make this a little bit bigger. We can see for high grades here for the two courses. So let's say a B or better at 0.8 or above. So here's, if you see where my mouse is, 0.8 to 1, 0.8 to 1. We can see that if there was independence, then probabilities of actually getting a B or better for both courses jointly would be higher than what it actually is in terms of the red surface here for our original f of x, y. So in other words, if you have independence or dependence, it does matter what's going to happen to these probabilities associated with these grades here. Okay. Okay, so that is an introduction to joint PDFs. Joint PDFs gives us probabilities associated with more than one random variable at a time. At times, though, we would like to just look at one of the random variables, and to do that, we can find the marginal PDF. Other times also, we would like to say, given a particular value for one of my random variables, what's my probability distribution for the other random variable? That's where conditional PDFs come in. And lastly, we also looked at the concept of independence and how that how that affects corresponding probabilities.